Hello everyone. This is topic number 8 for exam 1. I call this integrals of the other 4 trigonometric functions because if you think about the integration formulas for the 6 trig functions, we refer to them as the antiderivatives of the derivatives of the 6 basic trig functions. Here's the integration rules from Calculus 1, the list, and just to remind you of the table, the reason why we call them the antiderivatives of the derivatives is because we start with the 6 basic trig functions, list their derivatives, and then adopt their corresponding integration formulas. So notice amongst this list, we don't have a formula for tangent, we don't have a formula for cotangent, and we don't have a formula for secant or cosecant. So that's why I refer to these as the other 4. And so we'll state the formulas here. These are the chain rule versions. Got to have the standard disclaimer, let u be a differentiable function of x. And so we're going to prove this momentarily. The integral of tangent of u with respect to u turns out to be minus the natural log of the absolute value of cosine of u, and then plus our constant, of course. Then we have the integral of cotangent of u with respect to u, which is the natural log of the absolute value of the sine of u, plus our constant. So that's tangent cotangent. Now secant cosecant. The integral of secant u with respect to u turns out to be the natural log of the absolute value of secant u plus tangent u plus our constant, and then the integral of cosecant of u with respect to u is minus the natural log of the absolute value of cosecant u plus cotangent u plus our constant. So formulas that you probably wouldn't expect, a little more obscure, and we're going to see the proofs now. We're going to prove these with respect to x because we're going to actually make a u substitution. And within the context of the proof, having to state the theorem is actually a hint, because if we start with the integral of tangent of x with respect to x, and knowing that this has to be a given, that it's equal to minus natural log absolute value of cosine of x, the only way this integral could have resulted in a natural log is if it came from the formula for the integral of du over u, which turns out to be the natural log of the absolute value of u plus c. So it was a fraction. And then it's, moreover, whatever that denominator of that fraction was had to have been the u, which in this case is the cosine of x. So that's actually inherently a hint as to how you want to start the problem. That is, you want to express tangent as a fraction with cosine in the denominator. And we actually do know that tangent is equivalent to sine over cosine. So we'll write the integral of sine of x over cosine of x with respect to x. And now we'll start a u substitution in an attempt to fit the form for du over u. And we'll choose u to be the cosine of x. A du would be minus sine of x times the differential dx. Modifying by the negative, we have that negative du is the sine of x times the differential dx. So now looking at the function, what we have, the denominator was chosen to be u, the numerator sine of x dx, compare it to our du, and we see it matches, just modified by the negative, and so therefore replace that by negative du, and we make the change of variables, we'll bring out the negative, fits the form for du over u, which we can then integrate to get the natural log of the absolute value of u, plus our constant, and finally back substitute minus natural log absolute value u is cosine of x plus the constant, and that would end the proof. So kind of a nice little proof. And to prove secant, there's a little trick. Same idea though, the fact that it had to have come from du over u because it's a natural log, but then moreover, this quantity, secant x plus tangent of x, had to be the u, which was the denominator of that fraction. So there's a little trick here. And the trick is to start with, you start with what's given, the integral of secant of x with respect to x. And the trick is to multiply the numerator and denominator by the quantity secant of x plus the tangent of x. And make sure you realize it's plus. So that's what we're going to do, as we've discussed in terms of fitting that form. That's going to result in that integral. And I'm going to express this as secant x over 1. There's my multiplication symbol, this fraction. And multiplying, the trick is secant x plus tangent x in numerator and denominator. Now the dx should be off to the right. Now remember, with these proofs, everything counts. So at that point, what we're going to do is this. You can put parentheses around these quantities if you want, but the way I wrote it with the multiplication symbol, really not necessary. But we're going to distribute that secant that's in the numerator. So make it a single fraction. The denominator is just going to be secant of x plus the tangent of x, because 1 times anything is itself. When we distribute that secant that's in the numerator, we multiply secant by secant to get secant squared x, and then we multiply the secant distributed to the tangent, gives us exactly that, secant x tangent x. And that again is all with respect to x. So now we're going to make a u substitution. And we're going to choose our u to be the secant of x plus the tangent of x, the denominator. Because we're going to try to fit the form of du over u again. And when we calculate the du, because we're going to have 2 terms here, we need parentheses. And then we calculate the derivatives. Derivative secant, secant tangent, so secant x, tangent x, and then plus the derivative of tangent, which is secant squared x. Close up the parentheses and the differential dx. And that really is enough to see that it now matches. That is, the denominator was chosen to be our u, and the numerator, although it's in reversed form, by the commutative law of addition, is identically the du. Now, if you really wanted to, if you wanted to switch these around, so you could literally see it and write it as secant squared x plus secant x tan x, that would be fine, but it's not necessary because commutative law of addition is understood. No matter how you look at it, then, the numerator with the differential dx identically makes up du. And so we get the change of variables without any modification by a constant multiple, and we just add the integral of du over u, which integrates to be the natural log of the absolute value of u plus our constant, and then we back substitute. So natural log absolute value u was secant of x plus the tangent of x. And then don't forget to carry along the constant. Okay, so the next page is just, we're going to have a proof quiz on those two proofs. So it'll be announced in class. And the next page is just some examples. First example, simple case where it's fitting the form for the tangent of u, and u, the argument, is 5x. So the du is just 5 dx, modifying 1/5 du is the differential dx. So looking back at the integral, we already accounted for the tangent of u. The differential dx has to be accommodated, and that, compared to our du, matches just modified by the 1/5. So we get 1/5 integral tangent of u with respect to u upon the change of variables. Then we apply the formula. Tangent integrates to be minus natural log absolute value cosine of u, and our constant. And back substitute, we get minus 1/5 natural log absolute value cosine the argument of 5x and plus our constant. Now I wrote this off to the side here. In general, for k an element of the reals, we could then write that the integral of tangent of kx, okay, this is the linear argument rule that we've written before for like sines and all the trig functions and the integral v to the kx as well. Notice that if this were any number other than 5x, the whole thing is this linear argument concept that we've stressed many times. That argument 5x is linear. And when that happens, just imagine if this were, instead of a 5, it were a 7, these 5s would all be 7s. So if they're k's, then the integral of tangent of kx is minus 1 over k times the natural log of the absolute value of cosine of kx plus our constant. And this holds for all 4 of the formulas. So if you want to write them down, I guess we got enough room and certainly enough time. The integral of cotangent of kx. Okay, you get back the respective antiderivative, which is natural log absolute value sine, but because the linear argument kx modified by 1 over k, so 1 over k natural log absolute value sine of kx, then plus the constant. For secant, that integrates to be natural log absolute value of secant plus tangent, but because the linear argument modified by 1 over k. So 1 over k, natural log absolute value secant, same argument kx, plus tangent, same argument kx, and then plus our constant. And to write down the fourth one if you want, it's going to be negative 1 over k, natural log absolute value cosecant kx plus cotangent kx. Alright, so we want to be able to integrate by inspection if the argument is linear, because we're going to be seeing situations where that's going to be advantageous, and we don't want to have to go through the formal u substitution if we can get away with the linear argument rule. Just like in example 2, where we can integrate term by term, constant multiples tag along in the integration process using the linear argument concept. 3 tags along, the integral of cotangent is minus natural log absolute value of sine, but because of the argument 6x modified by 1/6, so negative 1/6 natural log absolute value of sine, same argument 6x. Then go to the next term, minus 10 tags along, and cosecant integrates to be natural log absolute value cosecant plus cotangent, but because the argument 5x modified by 1/5, so negative 1/5, natural log absolute value cosecant 5x plus cotangent 5x, okay, formally plus the constant, and then just making it look a little bit better here, minus 1/2 natural log absolute value sine of 6x, looks like plus 2, oh, minus 1/2 that is, then a plus 2 natural log absolute value cosecant 5x plus cotangent 5x, and then plus the constant of integration. So if the argument is linear, integrate by inspection with the linear argument rule. But if the argument is not linear, then we recommend a formal U substitution. And there's no change in our integration strategy, just the fact that we have these new formulas. But in terms of the integration strategy, when we have algebraics mixed with trigonometrics, we know trigs dominate. So we focus on that. If we have a basic formula for secant of u, now we know we do. We have integrals for all the 6 trig functions. And so we're going to choose u to be the argument 1 minus x to the 6th. The du is minus 6x to the 5th. Formally the differential dx. Modifying, we get minus 1/6 du is x to the 5th dx. Go back to the integral. We had already set up secant of u. Look at the leftovers, x to the 5th, differential dx. No surprise when compared to du that they match, just modified by the negative 1/6. So fit the basic form, change of variables, bring the negative 1/6 out in front. Integral secant of u with respect to u. Look at the formulas if you need to. Secant integrates to be natural log absolute value secant u plus tangent u. That negative 1/6 tags along, of course. And finally, back substituting minus 1/6 natural log absolute value secant of u is 1 minus x to the 6th, and then plus the tangent of that same u, and plus our constant. Sorry, I was running off the page there. Okay, so 2 more examples to finish things up. And with these formulas, I'm keeping them rather simple with respect to the fact that I'm only going to ask you questions on combinations of trigs, these trig functions with algebraics. I'm not going to put in exponentials and all kinds of crazy things, although we could, but I'll keep them pretty straightforward. But remember, with trig and algebraics, trigs dominate. So since I see the trig function in this problem, I'm going to rewrite this instead of over the square root of x. I'm going to rewrite it as the integral of 1 over the square root of x times the cosecant of the square root of x, to highlight the fact that the trigs dominate, and then I'm going to attempt to fit the form for cosecant of u by choosing u to be the square root of x, the argument of this cosecant. Now, we just have to exercise a little caution with regards to calculating our du. We first transform the square root of x into x to the 1/2. Now we differentiate to get du. That would be 1/2 x power 1 less negative 1/2, and formally the differential dx. We'll modify by the 1/2. You could think of dividing by 2, or excuse me, dividing by 1/2, or more efficiently, multiplying both sides by 2. So 2 du is equal to, and at the same time, let's get rid of the negative exponent on x to the negative 1/2 and write it as 1 over x to the positive 1/2. And if that's not enough to see it, then you could actually change back the x to the 1/2 to the square root of x. And what I meant by enough to see it was enough to see the fact that the leftovers, 1 over the square root of x, and the differential dx do in fact match the du, just modified by the 2, as we would expect. And so, making the change of variables, bring out the 2, integral cosecant u with respect to u, and integrating 2 tags along, cosecant integrates to be minus natural log absolute value cosecant u plus cotangent u, add the constant, and back substituting minus 2 natural log absolute value cosecant u is the square root of x plus cotangent of the same u square root of x, and then plus our constant. Alright, so one final example, and we're just seeing the fact that, you know, basic formulas when use a polynomial like number 3 is nice and straightforward, no chance for any really major errors. But you have to just be careful, like in number 4, when u is a radical, or like in number 5, when our u here, because trigs dominate, right? So we're still going to consider just tangent of u. Now u is a rational function, 1 over x to the 4th. So we modify by the negative exponent rule, x to the negative 4th. Our du is then negative 4x to the power 1 less negative 5. Differential dx as well. Modifying by the negative 4, we get negative 1/4 du is, at the same time, let's get rid of the negative exponent on x to the negative 5th, and we'll write it as 1 over x to the 5th. And now looking back at the integral, we've already established the tangent of u, the leftovers, 1 over x to the 5th, differential dx, compare them to our du, and we see they match, just modified by the negative 1/4. So we'll replace those by negative 1/4 du, and we can make the change of variables, so negative 1/4, integral basic formula, tangent u with respect to u, integrating, tangent integrates to be minus natural log absolute value cosine of u, plus our constant, of course, the negative 1/4 tags along, and back substituting and multiplying these coefficients, we get positive 1/4 natural log absolute value cosine. The u was 1 over x to the 4th, and then plus our constant. Okay, so that's it for topic number 8, and we'll see you when you're ready for topic 9.